everyone. Thanks for joining us for today's Tic Tech. Tic Tech is Alif Semiconductor's webinar series made for engineers by engineers. On today's webinar, we'll be talking to Plumerai and learning a little bit about the person detection demo they built and deployed on Alif microcontrollers. With me, I have Henrik Flodell, Senior Director of Marketing at Alif. Hi, Henrik. Thanks so much for joining us today.
Thank you so much for having me here, Alex. And thank you so much, Plumerai, for joining us. It's going to be fun to have a little chat with you and see what you've been up to.
And of course, we have Marco Jacobs on the line, Head of Product Marketing at Plumerai. Hi, Marco. Thanks so much for being here today.
Thank you. Looking forward to our call here. Yeah.
Great. So I'd love if we could start today by Marco sharing a little bit about Plumerai and what you do over there.
Sure. Yeah. All right. So Plumerai is all about making AI tiny. So we're a software company and we license our software, and we primarily focus on AI for smart home cameras and IoT. So currently we have these 4 AI models available. So on the top left, you see our people detection model. Top right here, you see our familiar face identification, which actually identifies people based on their face. Then we have vehicle detection on the bottom left, also combined with the people detection actually here, and we have a pet detection. So together, this is a full solution for smart home cameras. It's proven in production, running in the field. We train it with over 30 million images. The models are tiny, such that they can run on MCUs or small CPUs. And we really run our models on any platform, for instance, on ARM Cortex-A or Cortex-M. And here, of course, you probably know that Alif has Ethos-U enabled MCU, and that's what we'll focus on here. So, but first of all, I wanted to point you to our website, because on our website, it's kind of cool, actually. You can run our demos. So you just go to our website and you click on the people detection link at the top, or the familiar face identification link, and then you can run our AI right in the browser. And this is exactly the same software, the same AI model that runs on the Alif MCU. So it doesn't run in the browser.
That is actually really cool. I tested that feature, and it's impressive that you can kind of see the same result right in the browser there.
Yeah, let me show you maybe just a very quick demo here then. You just go to our website, you click on the link, you click on start, you allow your camera, and then we first, for the familiar face identification, have to enroll myself. So you type in your name, you sweep your face like that, just like on a mobile phone, and now it recognizes me. So if I walk out of view and I walk back into view, even at a bit of a distance, I just, as soon as it shows my face to the camera, then you can see it recognizes me. For instance, for a smart doorbell situation, you can recognize people at the door, see if it's a household member or a stranger. And the same model also did the people detection.
And these models that you have based these demos on and that you're running on the website, like you said, they are pre-trained by your data sets. So they essentially come from you ready to be deployed directly into a solution without having to do any further kind of tweaks to them. Is that correct?
Yeah, that's absolutely correct. So we collect our own data to train them with. We curate our data. We annotate this data. The first step is to have the best data available to train models. Then they're really our own models, so it's not an off-the-shelf model that's open source and downloaded from the internet. So we always optimize our own models for a specific use case, and to really make sure that they're highly accurate. And then we deliver this trained model optimized for a particular target platform. So here we did this optimization for the Ensemble MCU family. And then we license that as a complete solution to smart home camera manufacturers or IoT applications, a wide variety of applications, but especially in the smart home, we see a lot of possibilities to enable new use cases. Of course, there's a security use case, but also other use cases with our AI.
So Marco, you started to touch on this, but can you give us a deeper dive into what steps you took to actually build and deploy this model on the Alif microcontroller?
Yeah, absolutely. So here I have a high-level slide up here already, the different steps we took. So the first step is really to design and train an AI model that's optimized for the target architecture. So that was our first step. And then, of course, you have to integrate and port it to the MCU, integrate it with the camera capture, integrate it with the rendering, with the display. And the final step, of course, is to make sure it fits into memory. So I'll dive a little bit deeper into each of these steps. So this first task is really to design and train the best AI model possible. So the steps we took there is first, we worked with ARM, with the Ethos-U to benchmark the NPU. Every neural network accelerator is slightly different, is better at some things, worse at other things. So we benchmark it such that we understand what it's good at and what it's not very good at. Then we have our model template architecture. So we have a variety of AI models, and we look at which one then fits best that performance capabilities that NPU provides. So we then select the model. Of course, you also have certain performance targets. So, and then we train it. So we actually train it offline in our data center. We run our 30 million images through. We measure it, the performance on different validation data sets for different use cases. And then we select the final model that's then ready to be deployed on the Alif MCU. So that's the first step. The second step, so that's all around the AI model itself. The second step is to really do this software integration. So what we did here is there's the camera capture functionality, which is provided by Alif. Then there is always some pre-processing, so you have to scale the image. We do some intelligent motion analysis for kind of focusing the attention of the neural network on those areas in the screen that are interesting. That was all optimized for the Cortex M55 that's on board with the vector instructions. And then the model itself, we compiled with the ARM Vela compiler, which is quite a robust model compiler. So we compiled the model, integrated it with the code on the CPU for the pre-processing, and then finally we also have some post-processing. So, for instance, for our familiar face identification, there's this matching of the identified faces in the live view compared to the faces that have been enrolled in the library. So that all is post-processing. We also track people. So we don't just say, okay, there's a person here, but from frame to frame, we give a unique ID per bounding box such that you can track where people are going. So for use cases, for instance, if you want to count people or if you want to do perimeter detection, when do people actually cross a line, for instance, cross into your front yard or cross into a room, you need to understand where these people are moving. So for that, we have a tracker. So that's also part of post-processing that again runs on the M55.
And do you have a limit in these models on kind of how many people that you can perform these tracking operations on, how many bounding boxes that you can keep tabs on, or is that entirely driven by the resource constraints of the undefined device?
Yeah, of course, with bigger models, you can track more people. I mean, we focus really on the smart home use case. So we go up to about 40 people at the same time in view. So it's not really for huge crowds or so like a stadium, but it works very well in offices and retail or the home. So yeah, there's not a hard limit, but if you really have 100 people in view, then it won't work as well. Yeah. And then yeah, so we use the C++ compiler, standard compiler from ARM, and then for the model compiler, the ARM Vela, which was also freely available. So it was a very smooth process. Yeah, and then finally, I guess you could say this is part of software integration, but I call this final step making it fit, because what we found with MCUs is often they're very memory constrained, and this makes it hard. So just hard to develop software, and quickly you run out of memory. And just to give you a few numbers here, a VGA input image, which is not very high resolution, but for a lot of cases, VGA is a pretty good input image. Just a VGA input image is already 900 kilobytes. Our AI model, which is really really small and market leading in size is a little over 1 megabyte here for this demonstration. Then you have to execute this model, which also takes some memory while you're executing this model. You need some runtime memory. That's about 300 to 400 kilobytes. And then you have to render it, especially if you want to look at the results, of course. So then you need, again, a VGA frame buffer, again, 900 kilobytes. So if you add up these numbers, then quickly you see you need quite some memory. And this is for this tiny model that we have. Of course, this doesn't include yet the program code. So this making it fit is quite tricky. We can run on systems with very little memory, but it makes everything hard. So what we found nice about the Alif MCU is that it has quite a bit of memory available. This really eases development, especially as you work with images.
When we planned the Ensemble family of devices, one of the kind of goals that we had was to provide memory banks in the systems that are sized according to, roughly what type of cameras that we expected to be used together with the device. So we have a dedicated memory bank that is kind of intended to be a frame buffer for up to about 720p type resolution of a camera. We have another memory bank that can host something like a 1080p resolution coming in. And then we have additional memory in the system, like you say, for kind of the business logic, for the inference operations and all of that. So we try to make it as easy as possible because we realize that, when you want to try to move this type of functionality into an embedded device, memory constraints is going to be something that people run up against almost immediately. And they don't have that on the cloud side, of course. So this is something that everybody has to adjust their existing solutions to kind of work around on small scale devices.
Yeah, absolutely. So with other devices, of course, you have external memory, external flash, but that memory is usually slower, and of course it adds more chips, and that all burn power and add additional costs. So yeah, it's really nice that there's so much memory on the device itself.
All right. Thank you, Marco, for walking us through that. And I know this is the first time you had a chance to test this person detection demo on the Cortex M55 and Ethos U55 combo. Compared to other ARM-based microcontrollers you've tested, how do the results compare?
Yeah, so the Ethos U gives a huge uplift in performance. Here I have a slide that just shows some frame rates. So for instance, if you see for our people detection, we can run it on the Alif device at about 83 frames per second. And for the familiar face identification, it's about 33 frames per second. So this is very, very high. For most applications, 10 frames per second is really fine, which means there's plenty of headroom available, or you can go to sleep very quickly. So if you compare it against other architectures, here you see we can actually run on a Cortex M7, but then this model runs at about 2.5 frames per second. So that can be okay for like a presence detection algorithm where you just want to know if there's people in the room, for instance.
As long as somebody's not running past the camera.
Yeah, 2.5 frames per second gets quite slow quite quickly. You cannot count people indeed, or fast-moving people become a problem. Yeah. And we've also done work on an M85, which gives a higher performance point, but not very high yet. So for a single person class, for the people detection, you can run at about 13 FPS. And then you get really to the higher frame rates. You need a Cortex A class device typically, which of course is a much bigger CPU that runs at much higher frequencies compared to the Ethos U. So you see here going, especially from this Cortex A53, so this is actually a Raspberry Pi 3. So that's a
it's a pretty beefy system.
Yeah, exactly. Quite beefy with external memories and of course, very different type class of system but you see the Ethos U55, so at a third of the clock, it gets about 3 times the performance. So you could almost say it's one order of magnitude, almost factor of 10 more performance on a very different system, of course, on an MCU that boots fast, that doesn't need to run a full Linux system. So this very fast inferencing really enables you to run either more accurate, larger AI models, or multiple AI models, which we see a lot of use cases where you need to run multiple AI tasks. So of course this headroom provides that capability. And thirdly, especially for battery-operated target applications, and you can go to sleep very soon. So maybe the system wakes up from a PIR motion detector, thinks there's some motion, maybe there's a person in view. You just need a couple of frames to look at, is there really somebody in view? If not, you can go to sleep again. And just this rapid cycle that you can go to sleep very quickly, and you're only up during your duty cycle for a very brief moment of time. This means you can run for a long time on a battery, let's say years. You can build a system that runs for years on the battery. And this is especially important because as we are, if you want to roll out people sensing devices, pulling cables for power is a very costly exercise. You need to, people need to equip their buildings with new wire lines, and that's very costly, and it's not easy to install. It takes time. So of course, battery-operated devices are we find them very exciting because you can very quickly roll out many cameras in each room or around your house, and you don't have to charge them very often at all.
Yeah. So I mean, and these are really some excellent numbers, and makes me very happy to kind of see this, of course, and kind of this relationship between being able to perform fast inferencing and then go to sleep sooner so you can sleep longer and save more power. That's, of course, kind of a story that we've been telling. But I'm curious, based on kind of the deployments that you've seen of your machine learning models, if being able to unlock this level of performance, just in terms of kind of inference frame rates, if that makes it possible for you to address some specific applications that you kind of thought of, but that you had a harder time being a fit for because of limitations on the inference rate in particular. I don't know if that's something you can comment on.
Yeah, I mean, battery is always a better. Being able to run on a battery for years is of course both in consumer applications like a smart home camera is very nice to have. But we also see applications in smart retail, for instance, where you want to count people in stores, count people in front of digital signs to understand how often do people see the digital signs. There's smart city applications in traffic. There's smart buildings where you, of course, want to save energy. So you want to turn off the lights as quickly as possible, turn off the AC as quickly as possible when there's no people in the building. So it's about saving energy in smart buildings, and understanding where the people are in the building is good for safety, but can also save a bunch of energy. So these are just some of the applications that we see, but there's really a wide variety of applications. But smart home, our vision is that you really have a tiny camera in every room. And this also allows you then to be very safe. There's healthcare applications, for instance, if you understand where people are in the room, but especially also to save power.
So Henrik, does this align with the benchmarks you've measured internally at Alif Semiconductor on the Ethos U55? And can you possibly provide some more color as to what makes the Ethos U55 so much more efficient for inferencing?
It does. It aligns very well with both kind of what we are seeing, but also what the goal was when we went ahead and kind of spec'd out this platform. Because really what we wanted to get to, I'm going to kind of step through a slide here that has a couple of animation elements to it to just illustrate a little bit of what it was that what we saw and what we were trying to address. So when Alif set out to design the architecture of the ensemble devices, this is kind of the market situation that we were looking at, that you have in terms of performance, right, for machine learning solutions. There are some very, very high performing solutions. But these are cloud oriented architectures. These are things that run on servers. They're designed to be able to be heavily parallelized. There's really no constraints in that environment. If you want to run an outrageously large model, throw more service at it, that type of thing. So power is not a constraint. Memory is not a constraint. There really doesn't exist constraints in that environment. That's not an edge-based environment at all. There's been some attempts, some more successful than others, to kind of migrate these platforms down in terms of not, with the purpose of making them perform less fast, but more to try to scale them down into packages and formats and module sizes that make them more suitable for edge applications. But what we saw was that even though that's something that was going on, the solutions tend to be more complex than traditional microcontrollers because, the design constraints now that you place on that embedded device, you have the need to do very many layers in your PCBs. You have to have heat sinks in the operations. The modules are very expensive. Then there was this big gap kind of where there really wasn't any suitable solutions until you got down to the traditional 32-bit microcontrollers. And traditional 32-bit microcontrollers, when people talk about tiny ML, that's kind of what they mean. It's small machine learning models that can run on smaller devices. There's, of course, a lot of legacy microcontroller vendors that provide those devices, and they can run tiny ML just fine, those type of solutions, but they tend to be a little bit limited in what they can achieve, right? You can only do certain things at a reasonable speed. I mean, if you want to do something like traffic analysis, like Marco showed, you run that on a Cortex M7 and you have fast moving cars, you're probably not going to catch all of them. So this is kind of what it looked like. We had this big gap, and we figured that this is an area where we can come in and we can innovate and we can try to close this gap and make it possible to deliver 32-bit microcontrollers that can still be powered by small batteries, but that can give you this inferencing performance that gets close to the derivatives from the cloud processors, and really provide an uplift for the embedded designs to really kind of have a family of devices that are targeting the edge space. And there's a lot of numbers on this slide. I'm not going to show all of them, but kind of the key thing, and Marco alluded to this as well, if you inference fast, you can sleep longer. We benchmark this number here. This is essentially the energy that it takes to perform an inference operation. And we've run, this is not all of the benchmarks we have a ton more. So, feel free to reach out to us if you're interested in something in particular. We don't make machine learning models at all. Companies like Plumerai AI are experts at that, but we run this on open source models. And we train those models on open source data sets just to kind of see what does it cost to perform an inference when you're running this model? And then people that are well-versed in AI, they can extrapolate from there. If I do the experiment on MobileNet V2, then they kind of know that on my model, it should be, plus minus, whatever that parameter is. But the key thing is kind of, if you look at something like this, the energy, the number of millijoules per inference that you spend on a MobileNet V2 classification on an Alif device that is accelerated using not only the Helium vector instructions that come with the M55, but also by the Ethos U55 accelerator. I'm spending less than a millijoule per inference. If I switch all the acceleration off and just run it on the core, all of a sudden, now I'm spending 62 millijoules per inference. If you want to run a couple of thousand inferences, per duty cycle, that adds up. That's going to eat up your battery really quickly. So both in terms of time and in terms of energy efficiency, having a microcontroller that is built with the ability to accelerate machine learning really pays off for edge devices. And, it enables a lot of use cases to kind of operate better on fast moving data, I like to call it, and also to be able to conserve that battery so that you can last longer. And also, a lot of the customers we talk to, they're trying to design seamless technology. They want this stuff to be integrated into people's lives in such a way that they don't really, notice that, it was a machine that provided me with that information. And that never works if you have latency in the system. If you have a personal assistant at home and you ask them to turn off the lights in the bedroom and it takes 5 seconds before you get a response, that's enough time for you to get a little bit frustrated about it. So it's important to kind of try to tune for performance in these use cases.
Thanks, Henrik. It's really great to see what can be achieved with the M55 and U55 combo. Marco, I believe you actually have the person detection demo there with you. Can you show the viewers?
Yeah, exactly. So I just plugged in the power here, so you can see how fast it boots, and here you see that it recognizes you guys as people. That works well. It's the exact same, like I mentioned to you, it's the exact same model that runs on our website. That there we compile it for JavaScript WebAssembly, but we compile the exact same model for the Alif device. So you can test the robustness in your own home or behind your desk. Yeah.
And if somebody actually wants to get their hands on one of your demos and deploy it themselves, how do they actually get started with Plumerai?
Yeah, absolutely. So we have a demo application available for the Alif board. So if you have the board already, or you want to order the board online, then just fill in our contact form, reference the Alif board, and then we'll send you an eval version. Yeah.
Okay, great. And Henrik, is Alif hardware available for our viewers to purchase today?
Absolutely. It is available for purchase from Aero Electronics Worldwide. They stock our evaluation boards, the board that Marco showed you, as well as some other options depending on kind of from which direction you want to do evaluation. And also, of course, the devices are available from that you're looking for specifically. If you want to run it on the board that Marco had, is our AIML app kit. You can also go to our website, alifsemi.com. On there, you will find an order section, and that section has more information about what boards are available, what devices are available, configurations, and all of that good stuff.
All right. Well, thank you, Henrik. Thank you, Marco. That's it for today. So we'll see you next time. Thank you.
Thanks, everyone.
Thank you.